All right, let's get started with Unit 4. This is going to be something very different than the things that we've been doing. So in 4.1, the I can statement is I can understand function, vocabulary, and concepts. So let's write the word function right here. So function, vocabulary, and concepts. And we are going to be learning a lot of new vocabulary. The concepts that we go over, a lot of that is going to be review, I'm hoping. I'm hoping you've seen some of this stuff before. So let's start with the warm-up here. It says, what does the word function mean in the context of the following sentence? So it says, the function of an elevator is to get you from one floor to another floor. Well, I mean, that's just what an elevator does. That's what it's designed to do. So function means what it does. And I'm going to put designed to do in parentheses here. Designed to do. So that's what a function is. A function is a function of a particular item or machine or elevator in this case. It's what it does. It's what it's designed to do. Now last year you would have learned, or I'm hoping last year in a previous course, you would have learned that a relation is a set of ordered pairs. Set of ordered pairs, and it can be expressed a lot of different ways. It can be expressed as a mapping, a table, a graph, or a description. And there's really nothing special about a relation. Any set of ordered pairs will do. So I've got a set of ordered pairs right here. You'll notice that they're in the nice set brackets, and we can put those in a table. So I'm just going to take this one right here, and I'm going to go ahead and put -5, 2. Let's see, I need to fill in the x value for this one, so this would be -1. We've already got the 0, 1 there. This would be 2, 1, and this would be 4, 4. So I can organize those as a set of ordered pairs. That's fine. Maybe that's useful, but it's also very useful to have in a table. So we've got a set of ordered pairs, we've got a table, and right here I'm going to do a mapping. So I'm going to put the x's right here, and I'm going to put the y's right here. So I'm going to have a -5 and a -1. Sorry, I apologize. That's going to be a 2, so the 5 corresponds to the 2. And then we draw an arrow like this. Now you can put an arrow on the end if you want. You can just draw a line from one to the other, but then we're going to do -1 to 4, like that. We're going to do 0 to 1. And then we're going to do 2 to 1. And here's where something interesting happens. We really don't need to put another 1 here. What we could just do is we could just say, look, this 0 corresponds to 1, and this 2 also corresponds to 1. So that way we don't have to write extra values there. And then this 4 corresponds to a 4. Here's another one that would correspond to that one right there. So that one's totally okay. And then we can also graph it. We can draw a picture of the set of ordered pairs. So we've got our axes set up right here. So we're going to do -5 and 2. So that point there. -1 and 4. So we're right here. 0, 1. Again, we go right or left first, and then we go up. It's always the x coordinate, then the y coordinate. And over 2 and up 1. And then over 4 and up 4. So it looks like this. That's what our graph would look like. Now, this down here, we're going to leave this for a little bit later. We're going to learn some vocabulary. We're going to slide down here, and we're going to take a look at the rest of this. So some other things that we learned about relations are that if they're special enough, if there's some special condition that's met, we can actually call a relation a function. So for our purposes, a function is a very consistent mathematical rule that creates a set of ordered pairs. And because that function is so consistent, each x can correspond with only one y. Now, when we say correspond, we're going to try and change the wording on this so maybe it makes a little bit more sense. So let's write it like this, and you'll notice that we've got a box around this. So let's go ahead and put a star right here. This is probably a good thing to remember. A function is a set of ordered pairs. Now, if we stopped right there at set of ordered pairs, that would just be a relation. So here's the condition that makes it a function, where each x can be matched up with only one y. So every time we have an x, it can only match up with a particular y. It can't match up with different y's, and we'll look at what would happen in that case a little bit later on. So because functions are such a huge part of math, we've got some vocabulary that we need so that we can deal with these the right way and so that we can have some common language here. So the first thing we're going to talk about is the domain. So write domain here. The domain is the set of numbers that you plug in. So if we put something into a function and then it does some math to it, we call the number that we plug in, we call that part of the domain, and we call the number that we get out, we call that the range. So we're going to have domain and range. Domain is the set of numbers you plug in, and the range is the set of numbers that you get out. Now, if you think about it, you've actually used functions already. When you first learned how to graph linear functions, you probably did an xy table, you plugged in an x, and then you got the y, and then you graphed that. So what that means is most of the time the domain is the x's, or the domain are the x's, and the range are the y's, because we plug in an x and then what we get out is we get out a y. So what we're going to do is we're going to go back up to this example up above, and we're going to figure out what the domain is and what the range is. So remember, the domain is the set of x's. So the domain, what we plug in, and I'm going to do my set brackets right here, we can plug in a -5 on this one. We can plug in a -1. We've got an x of 0, we've got an x of 2, and we've got an x of 4. And then I'll close that set bracket right there. And then the range on this one is a little bit interesting. So notice that we've got 5 different x's, but we've only got 4 different y's. Now, if you want to take the time to write these in order or something like that, that's totally okay. But I'm just going to write them in the order that they come in, 2, 4, and 1. And then we'll close off that set of brackets right there. Again, I mentioned before I write ugly brackets, so you just kind of have to deal with it. All right, so these are the different ways that we can write down that set of ordered pairs. We've got a table, we've got a mapping, we've got a graph, we've got just that plain old set of ordered pairs, and we can also break it into the domain. Those are the set of the first ones, the x's usually, and then the range, those are the second ones. That's going to be the y's. So we're going to come back down here, and we've got some more vocabulary. We also call what we plug in, so usually the x's, we call that the independent variable. The independent variable. And so if that's what we plug in, then what we get out is called the dependent variable. So what that means is usually x is going to be the independent variable, and that means y is going to be the dependent variable. Now, there's a good reason why we like functions better than just plain old relations. So we're going to take a look at why we really want it so that each x can only correspond with one y. So here's an example for you. It says, suppose a function took the number of hours you work and calculated your pay in return. So the function is designed to do something. It's designed to take the number of hours you work and then multiply it by whatever you get per hour and then return what you get paid. So the hours that you work would be the independent variable. Independent variable. Okay, so you figure out how many hours you work, and then the amount that you are paid, that would be the dependent variable. And that should kind of make sense because the amount that you get paid is going to depend on the hours that you work, not vice versa. Okay, so we've got to work the hours and then we get paid for that. So it says complete the set of ordered pairs by following the pattern. So the pattern is 0, 0. And let's stop and think about this. If the hours are the independent variable, this right here is hours. So the x, so to speak, is the hours, and then the y is going to be the amount that we get paid. So if we work 0 hours, we get paid $0. That kind of makes sense. If we work 1 hour, we get $20. If we work 2 hours, we get $40. So you can kind of see the pattern here. So if we work 3 hours, well, if 1 hour is worth $20, that means this is going to be $60, and 4 hours is going to be worth $80. Pretty good chunk of change there. Okay, so let's write down what the domain is. The domain would be 0 and then a 1. Remember, we're writing down the independent variable. We're writing down what we plug in, the x, so to speak, and then a 2, and then a 3, and then a 4. And that's as far as this particular set of ordered pairs go. I'm sure we could continue that on if we needed to, or they told us that we need to. And then the range would be this. We get 0, 20, 40, 60, or $80. Okay, so on this one we happen to have 5 elements in the domain and 5 elements in the range, so everything's good there. And then the question is this a function? And if it is, we want to go ahead and graph it. We want to make sure that we scale and label the axes appropriately. So what we want to do is we want to make sure that each x corresponds to only one y. Well, there's an x, so to speak, a 0, and it corresponds to 0. Okay. Now, none of these other x's are a 0 either. So if we don't have any repeated x's, then there's no way that it can correspond to more than one y. And I'll show you an example of how we can mess this up in just a minute. So we're going to say, yes, this is a function. So we're going to go ahead and graph this. So remember, this is hours over here. That's like the x-axis. And this is the amount of money that we get paid. So let's see. Let's go ahead and count this as 0, and then 1, 2, 3, 4, 5, 6, 7, and so forth hours. And then we can't count by 1 here, so we're going to need to scale this differently, and hopefully it makes sense to everybody. Let's go ahead and scale this by 20. So 0, 20, 40, 60, 80, 100, 120, and so forth. And we'll graph this. So the first point is 0, 0. If you work 0 hours, you're going to get $0. If you work 1 hour, you get $20. 2 hours, you get $40. 3 hours, $60, and we can kind of see the pattern right here. Well, these are the values that we get there. I suppose we could connect that if we were told to. But again, we've talked a little bit about discrete and continuous. We're going to talk more about that as we get into this. So we're just going to leave those dots there. We're going to assume that we worked either 0 hours, 1 hour, 2 hour, 3 hours, so forth. Now, as an employee, so I'm going to change colors on this. As an employee, would we like it if they added the point 4, 20? So let's say we come up here, and I'm going to erase this right here, and let's say we add the point 4, 20. So we're completely changing this. And then I'm going to go ahead and graph this point. So 420 would look like this. Now, would we like this? No way. We would not like this. And here's why. There are times where we'd go in and we'd work 4 hours and we'd get $80. That corresponds to this point right here that lines up with the pattern. And then there's other times where we'd go in and we'd work 4 hours and we only get paid $20. Well, that doesn't seem very fair. Well, this type of inconsistency, the one demonstrated in this example right here, when we add this and this 4 corresponds to 2 different y's, that gives us a really easy way to tell whether or not a graph comes from a function, because none of the points are going to be stacked on top of each other. So notice this was fine. We could see that everything corresponded, every x corresponded to only one y, until we got this. These are stacked right on top of each other, and now 4 corresponds to 20, and it corresponds to 80. So this leads us to something called the vertical line test for functions, and you may have heard about that. So vertical, let's make sure we spell that correctly, vertical. So we flip the page over, and here's the vertical line test. And again, this should sound kind of familiar. The vertical line test for function applies to graphs. So if we look at a graph, any vertical line will intersect the graph of the function only once. So I've got a couple of example graphs right here, and it says, which of the following are functions? So here's what we do. We take vertical lines, so I could put a line right here. Well, it doesn't intersect it at all. That's okay. If I do it like this, it intersects it in one place, maybe right there, one place maybe right there, one place right there, one place right there, and so forth. So no matter what vertical line I draw, it only intersects this graph once. So what that means is this is a function. So we're going to use a little bit of shorthand right here. I'm just going to write F-U-N-C and put a period. So that means this one is a function, passes vert line test. Any vertical line will only cross it once. Now, I'm just going to go ahead and put down whether it is a function or not a function on this, but this is the reason why. And if we take a look at this right here, I can draw a line right there that intersects it in 2 places, and that's enough to tell me that this is not a function. So this x corresponds to 2 different y's, one up here and one down here, and that's not okay. So this is not a function. Okay, so I'll just write this. We'll circle that, and then we come over here. Again, notice that any vertical line will only intersect it once, so this would be a function. So the vertical line test is a really easy way to tell whether or not the graph came from a function. So let's slide down here and take a look at some other things. The other thing we want to be able to tell from looking at a graph is we want to be able to figure out the domain and the range. And that's actually pretty easy to do using the squish technique. So here's how the squish technique works. If we squish the graph onto the x-axis, then we're going to find the domain. And let me show you what I mean by squish it onto the x-axis. Take all of these points and push them up or down so that they're on the x-axis. So I'm going to put this push that point down. I'm going to push this point up. I'm going to push this point down, this point up, and that one happens to be right on there. So the domain of this one would be, that's right on -5. So -5, that's at -3, that's at 0. That's at 2, and this last one is right on 5. Okay, so we're going to go ahead and go like that. Okay, so we can do that for each one of them. That's the squish test to find the domain, and let's do these guys over here. Now notice the arrows on the end here. So these are below, so what I'm going to do is I'm going to take all these points and I'm going to squish them up here. So imagine this is kind of like a shadow. Everything here would be covered. Okay, squish this down here, everything there would be covered. And because the arrows continue going, we could take this and it would squish everything onto the x-axis. It would go all the way from way down here at -infinity, all the way up to here to +infinity. So that would be the domain on this one, so -infinity to infinity. So again, take this and squish it upward, squish it downward. And then this one right here, notice the big solid dot on the end here. If we squish this straight down, it would start covering from here all the way to there. So all of these would be covered. and then we'd squish these down here. All of those would be covered. So that's going to start at -5, and it's going to go all the way to infinity. Notice that arrow on the end there. Now, because that's a closed endpoint, we need a square bracket right here. So that's how you can tell what the domain is, by squishing everything onto the x-axis. So I'm going to come back here, and instead of squishing this onto the x-axis, we can squish it onto the y-axis, and that will find the range. So squish it onto the x-axis, push everything up or down so that it hits the x-axis, and that will tell you the domain. And now we're going to figure out what the range is. So I'm going to take these and we're going to squish them onto the y-axis. So I'm going to squish this one over here, this one over here, this one over here, and this one over here. So what that means is these points right there, those 4 points would be the range. So this is going to be, and I'll go from bottom to top. So we'll go -3, -2, 0, and 4. And you might want to stop and think about why there's only 4 elements in the range on this one instead of the 5 elements that we had in the domain. Remember, these two happen to correspond to the same y. They're different x's, so that's totally okay. It's still a function. And then on this one right here, again, we're going to squish this onto the y-axis. So we'd squish all those points over there, squish all these points over here. It's going to cover from way down there to way up there. So this is also going to be -infinity to infinity. And then this last one is kind of interesting. We've got this shape that starts right here, comes down here, and then goes up and continues going up. So if I were to squish these points over onto the x-axis, or the y-axis, it covers from 0 up to 5. These cover the same thing. So it's kind of like bringing these two sides together, covers from 0 to 5. And then if this continued like that, we just continue going up and up and up and up. So stop and think about what this is. If we think about the range in the y direction, we don't have any y's down here, but we start getting answers right there. So they start at 0 and they go all the way to infinity. We'll do a round bracket around the infinity and a square bracket around this one right here because it does actually hit 0. Okay, now we want to talk about one other thing that you can tell just by looking at a graph, and that is whether the function is increasing, decreasing, or it can be constant. And sometimes we'll have some weird combinations of those, but for the most part, we're going to be able to tell whether a function is increasing, which means the graph goes up from left to right. So as we move along the graph from left to right, does it go up or does it go down? If it goes down, then we call that a decreasing function. And if it stays the same, if it just keeps the same value all the way as we move from left to right, then we call that a constant function. So we've got an increasing, decreasing, and constant function. And we just want to look at this graph right here. And the instructions say this: determine if the graphs come from functions which are increasing, decreasing, constant, or NA. So NA would be not applicable, doesn't apply here, question doesn't make sense or something like that. So if we take a look at this, again, we start on the left side and then we go to the right side. So we start down here, and as we move from left to right, it gets bigger and bigger and bigger. The function values, the y values, get bigger and bigger and bigger. So this is going to be increasing. So increasing. Okay, which if you want to abbreviate INC, that would be okay with me, but don't say INC, don't say it's inc. Make sure you say the whole word that it's increasing. This one right here, you'll notice that as we go from left to right, it is perfectly flat. It stays the same value. The value is 1 here and 1 here and 1 here and so forth. So this is constant. Not much of a point to abbreviate that one right there. This one, as we go from left to right, it started way up here on that arrowed line, and then we go down here, so this is decreasing. Okay, so we'll go ahead and write DEC, but make sure you say decreasing. And then this one's kind of interesting. You will see quite a few graphs like this, maybe not in this class, but in the future for sure. So this one right here, as we go from left to right, you'll notice that it's flat, so it's constant right along here. Then it goes up, then it would be increasing, and then it would go down, then it would be decreasing. So what we're going to say for the entire function is you can't just categorize it as increasing, decreasing, or constant. Those words really don't apply on that entire domain from one end to the other. Okay, let's take a look at this thought experiment right here. It says true or false. All functions are relations. And the next true or false question is all relations are functions. Well, let's think about this. Remember, a relation was a set of ordered pairs, and a function was a set of ordered pairs with a specific condition on it. Each x could correspond, or meaning match up with only one y. So if you've got a set of ordered pairs, it's automatically a relation. But if it's a set of ordered pairs that has that special condition where each x matches up with only one y, then it's a function. So all functions are relations. Let's reword that. All functions are sets of ordered pairs. That is true. If we come and look at this one says all relations are functions. So all sets of ordered pairs are sets of ordered pairs where each x matches up with only one y. Well, if you just said you've got a set of ordered pairs but didn't add that condition, you can't say for sure that it's a function, so we would say false there. Now, what I'd like you to do is I'd like you to look at this self-assessment right here. I can understand function vocabulary and concepts. So we're talking about the vocab of increasing, decreasing, domain, range, all of that sort of stuff that we've talked about. Kind of rate yourself on that scale, and then we're going to take a look at problem number 3 from the practice worksheet. Okay, so we've got the worksheet open here, and let's take a look at problem number 3. You've got several problems like this. It says graph each equation, so they're all going to be a relatively easy equation, one that you're familiar with. It says state the domain and range using interval notation, so that's important. We want to make sure we're using interval notation. Then determine whether the equation represents a function. If it does represent function, state whether it's increasing, decreasing, or constant. So here's the equation that we want to graph. So this is a linear equation. You'll notice the slope is 1, so it's going to cross at -4, rise 1, run 1, so it's going to look something like this. So again, we want to draw from one edge of the graph to the other edge, put an arrow on it, and again, this is why those arrows are important, because the next thing we're going to talk about is the domain. So remember, this continues going in this direction. So if we were to squish this graph onto the x-axis, even these points that are way down here would come up here, and they would cover all of this x-axis right here. Every bit of this would be covered. Okay, so I'm going to kind of shade that in right there. Okay, all of these would be covered as we squish these graphs up toward the x-axis. And then if we take all of these points and squish them down toward the x-axis, all of those would be covered. And again, there are arrows on the end, so this would be from -infinity to infinity. Okay, always round around those. And then I'm going to come back here, and now we're going to find the range. So we squish this onto the y-axis. So these points would come over here, they'd get squished on there, and they'd cover that part of the y-axis. All of these points up here would get squished onto the y-axis. So this one would cover here, this one would cover here. So all of these would cover all the way over there. So even these points that are up here on this line, if we trace those over, it would cover the entire y-axis. So again, starting way down here, going all the way up there. So that would be from -infinity all the way to infinity. Now, is this a function? Well, if you've got a graph, it's pretty easy to tell whether or not it's a function. It passes the vertical line test. So we're going to say yes on this, but I'm going to challenge you just a little bit. We can kind of tell that this has got to be a function because every time we plug a number in, all we're doing is subtracting 4 from it. You're never going to plug in a 10 one time and you get a 6, and then the next time you plug in a 10, you get 22 or something like that. Kind of like when we went in and worked 4 hours and we could get paid two different things. When you plug in a number, you always only get one number out. So you can kind of tell by this one also, but we won't get to that point yet. And then it says a description, is it increasing, decreasing, or constant? Because this is going up from left to right. As we move from left to right on the graph, we go up, so this would be increasing. Okay, there's how you do that. I am going to flip over to the back side because there's some that look familiar, and then there's some that are actually going to challenge your thought a little bit. That's what this is for, so take a good look at it. There are several places where you can practice the vocabulary, so good luck on the assignment.